Hello, welcome. Thursday, week 2. So, I was just saying before the recording started, but it's worth bearing in mind now. So next week is week 3, and 2 important things happen in week 3. The first is that your first online quiz is due. Now, I assume by now you've noticed that some of the assessments in first and second year have been labeled as early feedback tasks. These are basically like if you don't do it or somehow manage to get 0 on this test you get to do 3 times over and over again, then we email you and be like, hey, what's going on? Is everything okay? If things get on top of you and you don't fill it out, don't panic when that email comes. Just let us know what's going on. We want to try and make sure that you are engaged with the subject. That's the purpose of the quizzes in general, and particularly the early feedback one. The other thing that's going to happen is tomorrow I'm going to upload assignment 1. Or the assignment, because there is just one assignment. It's not bad, but it is obviously much more tough than the online quizzes. Take your time, do it as a group. To give you some idea, the first 2 questions are kind of like the sorts of questions you might find in a textbook, possibly on the challenging side, but essentially like, here is a question, do the question. The first one is about constructing tangent spaces. The second one is about multiple integrals, which we will start next week. Questions 3 and 4 are a little bit different. Questions 3 and 4 are taking stuff that you've learned and putting them in a mathematical context that you haven't seen yet. So they are sort of stepping you through results that you will encounter throughout your mathematical studies. The third question is a question about Lagrange multipliers, which puts it in the context of geometry and linear algebra. And the fourth question will be a question on multiple integrals, which actually constructs a very famous solution to a partial differential equation, which you will meet in your studies down the track. These are nice results. The answers are out there. I didn't make them up. The formulas you come up with have names. That's fine, and you will probably find them if you do a lot of reading or, Wikipedia the name of the formula. But, have a go at doing these things on your own. The purpose of an assignment is kind of not to tell me what you know, but to tell you what you don't know. So have a bit of a go and see if you can work through it on your own. But, as you know, these are assignments. I'm not in your room watching what you look at. Get the answers any way you can, but try and get as much value out of it as possible. All right, so what are we going to do today? Today we're going to wrap up the optimization that we did yesterday, which hopefully was a bit revision-y for a lot of you. We're just going to prove the classification theorem, which will be about the first half hour, and then we're going to move on to constrained optimization, or Lagrange multipliers. This is an incredibly powerful technique that you use again and again and again in mathematics, so it's a nice thing for us to cover. But before we do, let's wrap this up and let's prove the result, which is the classification proof. We're going to prove it in 2 variables. The proof pretty naturally extends to n variables. You can do that on your own if you want, but just to keep the slides bearable, we'll restrict it to 2. Unsurprisingly, a little bit of linear algebra. I mean, we're talking about eigenvalues, right? So you'll remember from the distant history of yesterday, we learned that if we construct our Hessian, we can have 4 things happen. Both of our eigenvalues are all of our eigenvalues are positive, all of our eigenvalues are negative, our eigenvalues have both signs represented, or at least one of our eigenvalues is 0. And the sketch of the proof is going to require us to consider a function, a half lambda 1 x squared plus lambda 2 y squared plus what we call higher order terms. This is a bit of a mathematical shorthand, and what it means is terms smaller than everything we have, so x squared or y squared, in the limit that xy goes to 0, 0. And this is a multivariable limit, so of course it doesn't matter which way we approach, which means we're talking about terms like x cubed y to the 4, x cubed y to the 6, but not x, xy, even x squared y, because we could fix y and approach down x, which would mean it's the same size as x squared. So we are talking about things that are definitively smaller than this in the limit that we go to 0. This is a very common mathematical acronym. You'll see it often without explanation. It means all the things that are smaller and we don't care about. When you were doing limits in lecture 1, you were crossing stuff off. All right, questions, but let's keep them quick.
So we basically just mean that, like, the quotient goes to 0?
Yes.
Okay.
Question.
Why is x squared y bigger than x squared?
It's not bigger, it's the same size, because if we fix y and then approach down the direction that x goes to 0, then they are a multiple of each other. Their quotient is not 0, so that the limit is non-zero. Good, good. Great questions both. So this function here, we know quite a bit about. If lambda 1 and lambda 2 are positive in all directions from 0, this is a minimum. I haven't said what lambda 1 and lambda 2 are yet in this formula. Obviously, we will later relate them to the eigenvalues, but currently they're just numbers. If lambda 1 and lambda 2 are both negative in all directions, then f is negative in all directions, so it is a maximum. But if lambda 1 is positive and lambda 2 is negative, then in this function, if I go in the x direction, I increase. If I fix x and go in the y direction, then I decrease. So straight away we can see that I have both. This is positive in the x direction. This is negative in the y direction. And since we can, within a disk around the origin, catch things that are both positive and negative, what we have is a saddle. And finally, lambda 1 or lambda 2, we can't tell what's going to happen. And this is why it's inconclusive, because if these are 0, then working out the sign change depends on what's going on here. And we didn't even write down the third term of the Taylor polynomial, which we won't be doing. But you can see that if we want to unpack the inconclusive case, we need to go into the higher order terms, which is what you do in one variable, but it's trickier in multiple variables. So it depends on the higher order terms and is therefore inconclusive. Okay, so the aim is to take the general two-variable case and turn it into this case where we know all of our answers. So like many proofs in math, the aim is to take something general that we don't know and to show that it is equivalent to something specific that we do know. And we are going to do that, and we're going to set up the actual problem we care about. Now, we're actually going to do a bit of a shift. We're going to shift the geometry so that the critical point is at 0, 0. And that f of 0, 0 is 0. This is just a translation in all of our variables to put everything we care about at the origin. This is valid as we can always do that. I can always make the transformation x equals x naught plus u, y equals y naught plus v for any u and for any x naught and y naught, and g of xy equals f of xy minus f of x naught y naught. And you know, in this case, if we had a critical point at x naught and y naught, where the value is f of x naught, y naught, then in our new variables u and v, the critical point is at 0, 0, and the value at that point is 0. And if we think back to last week, the Jacobian of this transformation is clearly 1, because it is the Jacobian matrix will be the identity matrix. So translations don't do any stretching or squeezing, so nothing weird happens. We're just changing our perspective. So this is a without loss of generality situation. We can just consider things at the origin, safe in the knowledge that we could easily transform any polynomial to that. So let's pull back Taylor series, which we briefly met yesterday. But of course, we've made our life a bit easy. We've said f of naught naught plus gamma, nabla, f of naught naught, dotted with x, where x is x and y, as we note above, plus a half x, and then we had our Hessian, which we're going to write as d squared, just for analogy with Taylor polynomials, x tau, x transpose, plus higher order terms. Okay, so those are the first three. Question? right at the start, we said we have two smooth derivatives, and everything in the classification theorem says we can take two derivatives. We made that assumption, and we will continue to make that assumption. I need to keep teaching, guys, so there's 3 questions. Let's keep them quick. Yes, we're assuming enough differentiation to make this possible. We stated that yesterday. Next question. We're just stating the Taylor polynomial. We're not deriving the multivariable polynomial case. You can dig that up if you want, but it's beyond the scope of the course. Oh, well, beyond the scope of this lecture, yes. Yeah, that should be xt. Yes. No. I'm going to say use whatever works, because we, generally speaking, when it comes to coordinate vectors, just cram it in any way that fits. All right. Good? That was a question, right? No, it should be horizontal and then vertical. You should get a number out of this. Yeah. All right. We got all the assumptions out of our system? Okay. Sorry, I thought I saw a hand up at the back. Do ask questions, but be aware there's a lot to get through, so I may answer them quickly, and I may sometimes power through. Okay. So, we know some stuff. F of 0, 0 equals 0 by construction. We said that at the beginning. We've shifted our term to get that. We also know that from the definition of a critical point, f0, 0 dot x is equal to 0. Because, of course, grad of f is 0. So, this is by construction. And this is because 0, 0 is a critical point. Which means that our f of xy actually reduces to this nice little quadratic form, xy d squared f of 0, 0 xy. Okay, it's 2 variables. They go like that. And that spits out a number, plus higher order terms, which are going to be smaller, assuming that thing is not 0. Now we're going to have to cast back and use a result from linear algebra that we aren't going to prove, which is that our Hessian matrix, being symmetric, is very convenient because symmetric matrices are orthogonally diagonalizable. Diagonalization isn't going to be a huge deal in the first half of the subject, but it is going to be a very big deal in the second half of the subject. So this won't be the last time you meet diagonalization. For those who might have forgotten, an orthogonally diagonalized, or you might meet in 2922 in the intervening, an orthogonally diagonal matrix says that there exists some U, typically composed of the eigenvectors of A, but we don't actually need that information here. There exists some U such that U transpose is the identity, which is to say U's transpose is its inverse, and we can write A in this form. U transpose AU is equal to some diagonal matrix where its diagonal matrices are its eigenvectors. What you're basically doing to construct the diagonalization, and I'm going to leave the technical details to linear algebra, is that you are doing a change of coordinates such that each eigenvector is one of your coordinate directions. That's what diagonalization is. You are representing your space in the basis of eigenvectors. And that's what we do, but we basically just need this for the algebra, so don't get too lost on this. If this is something you're familiar with, great, and if it's not, it's a fact, and you'll probably prove it in James's class. Okay, so with that in mind, we're going to let U satisfy U transpose, and then our symmetric matrix that we care about is, unsurprisingly, the Hessian times U. So this is our A. Is equal to the diagonal matrix of the eigenvalues of A. And this is good because The eigenvalues of A are what we are interested in. Obviously, our result comes from the eigenvalues, so we're going to power through. So what we're going to do, I said that this diagonalization is functionally a change of variables. We're going to explicitly make that change of variables. We're going to say xy is equal to u times by some new coordinate, x tilde y tilde. So this is our general f, and we're doing a change of coordinates which will, as we discover, make our coordinates x and y point in the eigenvector directions. And of course, if we take the transpose, which we're probably going to want to do, xy transpose is going to be equal to x tilde y tilde transpose u transpose. By remembering that the transpose of a product also switches. Okay. So we do our change of variables, and our f of xy from before, which was a half xy d squared xy, becomes a half x tilde y tilde, which is our x, which is this, times by u transpose, times by our matrix A, which is of course the Hessian, and then on the other side, u x tilde y tilde. So this was this, and this was this. So we've just done a variable transformation. But now what we want to do is group these three things, because this is nothing but u tilde au, and remember, u tilde au is equal to the diagonal matrix of the eigenvalues. So this gives me a half x tilde y tilde times by the diagonal matrix of the eigenvalues, x tilde y tilde. And if I expand this out, then what I get is nothing more than a half lambda 1 x tilde squared plus lambda 2 y tilde squared. And of course, all of these have higher order terms that we also transformed, but because this is a regular, well-behaved problem, they're not going to change their order. Plus higher order terms. And this is exactly what we wrote down before, and we understand its behavior. If both of those lambdas are positive, then it doesn't matter what direction we go in, this will increase. If both of these lambdas are negative, then it doesn't matter what direction we go in, the value will decrease. But if those lambdas are different signs, then if I go in the x direction, it might increase, or the y tilde direction, it might decrease. So what I have essentially done is done this mapping here, this coordinate transform, which has moved me into a frame where if I go in one of my directions, I'm influenced by the first eigenvalue, and if I go in the other direction, I'm influenced by the second eigenvalue. So these, it turns out, as I mentioned, are the directions of the eigenvectors associated with each eigenvalue. And this is nice because then the result follows from the previous page. We've moved it into a form we know. Dot. Okay. A last statement about the classification theorem before we're going to leave it in our past and move on to constrained optimization is that probably when you did in first year the second derivative test, you probably looked at some cases where it breaks down and you probably got told, well, you know, let's actually look at the function and see what it does. And in fact, we did one like that yesterday, where we looked at the classification theorem breaking down, and we took a cross-section, and we were able to see that it's a saddle, because we were able to construct a cross-section which had both positive and negative values. There's no real systematic way to do this, and sometimes it's very hard, or even almost impossible. So let's take this surface here. So this surface is x squared plus y squared minus 2xy. And I've constructed this surface to be a bit mean. So if I look at the gradient and I just try and apply the classification theorem, find the critical points, I'm going to find that grad f is 2x minus 2y, 2y minus 2x. Which is not so much satisfied at a single point, so much as satisfied for all x equals y. So this is a little bit trickier. It's not totally obvious how to classify this. Now remember, this could still be a local maximum, it could still be a local minimum, it could still be a saddle. We don't know. So if we go, all right, I'm going to get my Hessian matrix and I'm going to check out its eigenvalues. The Hessian matrix is going to be 2 minus 2 minus 2, 2. And this has one eigenvalue, which is increasing. Well, one eigenvalue, which is positive. There will be an increasing direction. And one eigenvalue, which is 0. So there's going to be directions where it increases. And if you're smart, you can probably see that it's going to be this direction here. And there's going to be directions where we're not sure what's going on. And that's probably going to correspond to this direction here. Could it go up? Could it go down? Maybe we need to check out the higher order terms. Now, if I take just a cut and I'm able to find what's a single point where it has decreased, then I found myself a saddle. So finding saddles is actually okay because you just need to show that one point exists. But showing that something is a maximum or a minimum is a little bit harder because you have to show that something doesn't exist. You have to show that there are no points within the disk where the value has decreased. That's a bit harder because a cross-section doesn't tell you that. It only tells you if something does exist. If I take one cross-section and I don't find any points where the value has decreased, that doesn't tell me that on another cross-section that might not be the case. So I need to be a bit smarter, and unfortunately there's no easy systematic way to do this. If you ran into this situation, my advice would be plot it and see if you can figure out what's going on. Now, I can show you what's going on here because I can show you how this was constructed. If we let u equal x plus y and v equal x minus y, then in fact f of uv, once I make that transformation, is u plus v over 2 squared plus u minus v over 2 squared minus 2 u plus v over 2 u minus v over 2. Don't write that down, or do, I don't care, but it's not important. What's important is in this coordinates, f of uv is equal to v squared. And in this coordinate system, we can see quite clearly that what we had was a minimum. The test still fails, but this is clearly a local minimum at v equals 0, which is to say at x equals y. That was easy because I constructed it, but if you didn't construct it, you couldn't just sort of guess at this transformation to show that something is the case. This is one of the reasons why, as much as you can, some kind of graphical tool is really, really helpful once you start thinking of surfaces. Because the second you run into an inconclusive case, you either need to start picking away at the higher order terms, you need to get very lucky with a cross-section, or you need to come up with a mapping which is staggeringly convenient. But there's no recipe we can give you that will tell you how that thing goes. So classification in 1D was a pretty simple problem, but in higher dimensions there's just a lot more things that can go wrong. All right, that is all we want to do for unconstrained class. Nope, I've got one more example. So we're going to do one more example of unconstrained classification, but it's a useful one because it is no longer a geometric surface that we look at. It is something from linear algebra. Yep.
How do we know we need to do u equals x plus y?
You don't. Like I said, I constructed it so that would work, and I only happened to know that. That's kind of the point, is if you don't know that information in advance, you could never really easily calculate what's going on. Yeah, basically you don't know that. If I gave you that question, it would be horrifically unfair, and I wouldn't do that. Yes?
We can use AMGM inequality and all that.
There are obviously individual things that can work in convenient surfaces, but that's not a general rule that will work every time. All right, there's a little bit of chatter. Let me finish this and I will give you a break. All right, So, as I've said, one of the benefits of having this algebraic way of approaching things is we can talk about systems that we can't quite see. So I want to talk about this function det, which you might think is a determinant, and you'd be right. So if I give you a matrix AD minus BC, then what I'm really asking about is what is the determinant of ABCD? And I'm saying I want to know about this four-dimensional function, and I want to know when it is optimized. And this is going to be an interesting one because we're going to do a constrained version of this later on. But it's just a function of four variables. We can think of this as a map from R4 to R. And because it's a map from R4 to R, we can just do all of our tricks on it. So if I want to find the grad of the function det, that's going to be the derivative with respect to A, which is D, the derivative with respect to B, which is minus C, the derivative with respect to C, which is minus B, and the derivative with respect to D, which is A. And if I want to find the critical point, I just need to find where that is equal to 0. So hopefully you can see that this has a critical point at A equals 0, B equals 0, C equals 0, and D equals 0. Going to take a vote. Everyone's got a vote. Pick one. Doesn't matter if you're right or wrong. Who thinks that that critical point will be a local maximum? Who thinks it will be a saddle? Who thinks it will be a local minimum? Ah, you guys impress me. Let's prove that thing that you all figured out immediately. All right. Let's put together the Hessian. Okay, the Hessian is a pretty easy one to compute. 0, 0, 0. Minus 1, 0, 0, minus 1, 0, 0, 1, 0, 0, 0. And of course, that has the characteristic polynomial minus lambda squared minus 1, all squared, once we do the eigenvalue stuff. So the eigenvalues are 1 and minus 1, with multiplicity 2. And as you all noticed, this is a saddle. And we can intuit that it's a saddle, and you did, because if we increase A and D while fixing B and C, then the determinant grows positively. But if we increase B and C while fixing A and B, the determinant, I'm going to say, grows negatively, which is to say becomes bigger in the negative direction, which is to say becomes smaller. I just want to sometimes people think smaller is going to 0, and sometimes they think it's going to minus infinity. I want to be very clear, I mean the second one. So we can either make the determinant become larger, or we can make the determinant become smaller or larger in the negative direction by picking the direction in which we change A, B, C, and D. So that's quite nice. It's going to turn out that if we start to put restrictions on the determinant, as we will do with constrained optimization, then we can see some other neat results come from that. All right, you guys are a bit talky today. Take 30 seconds, get it out of your system. All right, start wrapping it up. Okay. All right, good. So everything I've taught you thus far should hopefully be sort of revisiony. Maybe you're a bit rusty, maybe you've forgotten since you learned it in 1962, but it should hopefully have felt a little bit familiar. I am reliably informed that what we are about to do is new material for you, but it's also conceptually a lot trickier. Well, a little trickier, incrementally trickier. But the idea is optimization, when you can just wander all over X and Y and Z and go anywhere, is a pretty easy problem. You just look for critical points and you point at them and you're done, and you don't have to worry about where you're allowed to walk. But a lot of problems don't look like that. A lot of problems are a bit more constrained. So instead of saying, well, what is, the maximum anywhere I might want to look at, I might want to say, well, if I am restricted to moving along this curve, what is the maximum value that some function takes? And you've seen problems like this in first year. A nice motivating question, which I imagine you've seen before, is if I have some line y equals ax plus b, I want to minimize the distance to the origin. Now, you can do this geometrically, just using trig rules. You can do this using any number of ways. But if you asked one of my first year students, hey, how do you do this? Then they would say, all right, we want to come up with a function of one variable, and then we want to optimize it. So the function that they might want to optimize is, say, d squared equals x squared plus y squared. Actually, 90% of them will try and do the square root, d equals, but we're smart. We know we can square it and make our life easier. So we want to minimize d equals x squared minus y squared, but we know that x and y have this relationship, y equals ax plus b. So we can write this as x squared plus ax plus b all squared. And then it's just an exercise in single variable optimization. You take the derivative, you set it to be 0. You can eyeball that it's going to be a minimum, but maybe you can't, so you do the second derivative test, and you're all very clever. And after a couple of tries, because you mess up the algebra, you get ab over 1 plus a squared is the value of x. And y is equal to, a times that plus b. Okay. But of course, problems get a bit harder, and we might need some more heavy-duty stuff for, when the dimensions become bigger, when we start to introduce vectors and matrices and all of that stuff. So what we're going to do is sort of unpack what's happening here and kind of see if we can rip apart the engine and just extract the pieces that matter. And we're going to do this using our good friends level sets. We're going to say that there is some function which has level sets. And in the case of this problem, that function is the distance. If I have my function d, then its level sets are circles of radius d. Okay, so we can see something quite nice, because if r is too small, if my d is smaller than this optimal value, then it doesn't intersect my line anywhere. If d is bigger, it will intersect my line twice. But if I've caught precisely the minimum, then, assuming everything is nice and continuous, I touch it precisely at a single point. And at that single point, I have discovered the optimal value. So if r is too small, then I get no intersections. If r is too large, then I get 2 intersections. But when r is just right, yeah, you all thought it, even as I said it, but I was trying not to make that joke, yes. When Goldilocks gets the r that is just right, what feature do they share? And what I want you to not say is the point. What is another property that the two curves have in common when r is just right? Yes. Tangent. Very good. When r is just right, the line and circle share a tangent plane. And I am saying plane here because it is stuck at P, but once again, it doesn't actually matter. We really mean the tangent space. But because there is an underlying geometry, we're going to go with that. So it seems like, considering the level sets of some function, is the tool that we're going to need to do this constrained optimization. But what we're actually going to do, we're going to do something even smarter for a while, which is we're kind of going to unfix this. We're actually going to define both of these as level sets. So one function will be a level set of our D, but this line will be the level set of a different function. Now you might go, okay, but if this is the level set of a different function, say maybe it can slide up and down, then I could come up with a construction there where they share a tangent, and you could. So what we're going to do is we are going to do equivalent tangent spaces of two level sets with an extra constraint that fixes one of the level sets appropriately. And those are going to be the ingredients of constrained optimization. So let's try and do this same problem using that idea. So our big question is, what value of r gives the same tangent plane as an intersection? And for a little bit of extra mathematical flexibility, we're going to write both of these as level sets. So we've met one of our level sets. We have x squared plus y squared equals d squared. So our level sets are described by d, x squared plus y squared. But we need a second level set. And I'm going to say there's some quantity L, which is equal to y minus ax. So this is the level set associated with my magenta curves. This is actually going to be a level set associated with blue curves, because I can also have curves like, they should be parallel, curves like this. And this special curve, the curve I care about, is the curve on which L is equal to B. Because if L is equal to B, I can take the AX over here and I get Y equals AX plus B. So what I've done, and this is quite a common technique in mathematics, is to think about a slightly higher dimensional problem that I'm going to restrict using a constraint to the one that I care about. This is going to be really important when it comes to solving differential equations, because you're going to come up with what's called compatibility conditions, which is saying, oh, I've come up with a much bigger solution set, and a compatibility condition brings me back to the ones that actually make mathematical sense. So this idea of blowing up into a higher sort of dimensional problem, which we have a bit more flexibility to work in, is a really common thing that you won't just see in the context of Lagrange multipliers. You'll see all through mathematics. It's a really common trick. And this might be the first time you're seeing it in action. Okay, so now I have two different functions with level sets. And these are two functions of x and y. You might say, I mean, you've isolated B here, but could you do this isolating A as the level set indicator? Absolutely you could. You'd get the same result. Worth a try if you're interested. But now we're going to do exactly what we did before. We'll calculate the two gradients, and we'll ask ourselves, when are the gradients of these two level sets the same? So the gradient of my d squared function is equal to 2x 2y, and the gradient of my L function is equal to minus a and 1. And for the tangent plane to be the same, we don't need these vectors to be the same. We need their direction to be the same, because remember, the tangent plane only cares about direction. So what we actually want is, for these, we want these to be some multiple of each other. Scalar multiple of each other. Because that means the tangent planes are parallel. And that's all we care about. So that will make the tangent planes parallel. For the tangent plane, let's even write that explicitly. To be parallel, we need that grad of d squared is equal to some constant times by grad of L for some lambda. You might at this point be going, lambda is a pretty loaded symbol. There are other situations, including ones we were just talking about, where lambda is an eigenvalue. Believe it or not, this is not an eigenvalue. It is the standard terminology you use in Lagrange multipliers. Except that's also a lie, because there are contexts, which you will discover in assignment, where this is an eigenvalue, but that's a thing for the future. As far as we are concerned, this Lagrange multiplier just happens to have an unfortunate symbolic coincidence with eigenvalues, and they are not the same, except when they are. Okay, so that was that highly, highly careful piece of warning there. We will not be treating this as the same thing. Okay, so in that case, let's just quickly do the algebra. 2x, 2y equals lambda minus a1, which tells me that they lie in the same tangent plane. Same tangent space. But we don't want any old level set. We want the specific level set associated with L equals B, a constraint. So we're going to say we want y minus ax, or if you like L, is equal to B. So here we are constraining it solution to L equals B. And this actually gives us three equations for three unknowns. We have 2x equals minus a lambda. We have 2y equals lambda. And from our constraint, we have y minus ax equals b. And if you solve all of those things, and I'm not going to waste a bit of time doing all of this algebra, which is to say I did this in Mathematica. 1 plus a squared, y equals b over 1 plus a squared. And you also get lambda, which is 2b over 1 plus a squared. There we go. We used tangent spaces and a whole extra dimension to solve a problem that my first years could have knocked out in 15 minutes. So there's got to be a good reason for this. And there is. In this problem, the constraint was kind of artificial. We sort of had to produce a constraint to do this problem this way. But a lot of the times your constraints are very natural restrictions. You don't have to do all of this work to construct a second batch of level sets or anything like that. The constraint is part of the problem a lot of the time. So let's talk about the general framework that we can turn this into. This was a motivating example, but now we're going to dial it back and say, well, what's the big picture here? The big picture here is if I have some map where f maps Rn to R, so multivariable function, and g maps Rn to R, and we're going to say that we want to know the extrema of a function f subject to a constraint related to g. So typically, f and g are given to you as part of the problem setup in some way. So just some function f subject to some constraint g equals a constant. You might say, what if g doesn't equal a constant? And I will say move everything to one side and let the constant be 0. It's fine. You can always just equal signs work that way. It's very convenient. You can always write a sensible constraint this way. Then what you want to do is you want to set up a rule about the tangent space, which is to say the tangent space of your function f should be some scalar multiple of the tangent space of your constraint. So same tangent space. Chris, if we're being sort of thoughtful, shouldn't it be the gradient of the constraint minus the constant? Yes. What's the derivative of a constant? It's 0. So we tend not to write that. You're not wrong if you do, but it's just not what we do. And the extra constraint, g equals whatever our constant was. So we want to enforce the constraint. Now, instead of a system of n equation and n unknowns, we've added an extra equation. We have a system of n plus 1 equations and n plus 1 unknowns. But you can still solve that with only plus 1 extra effort. So this tends to produce nice results. This tends to produce incredibly useful results. Almost, physics is made up, for instance, of governing equations and constraints, and this lets you combine them all in together. As I said, ODE solvability conditions give you constraints. Constraints are a big part of any practical optimization problem, and Lagrange multipliers give you a really nice way of dealing with those. So let's do a very simple example, and then let's move on to more complicated things. We like examples that are a thing we can visualize. It helps us visualize them. So we're going to say we have a bead of mass m that slides frictionless, because friction is for physicists, on a circular wire. So x squared plus y squared is 1. Our bead can't go anywhere. It's trapped. It can move around as much as we want. We're going to say our bead experiences gravitational potential energy, mgy. G is gravitation, m is the mass of the bead, y is its height. Find the equilibrium position of the bead. Equilibrium positions in physics tend to be positions that minimize potential energy. So what we're actually trying to do is to minimize the gravitational potential energy, i.e. minimizer of gravitational potential energy. So we need to minimize that, but we can't break the ring and drop the bead off to minus infinity. We're a bit stuck. Now, this is not a particularly difficult problem. Gravitational potential energy is proportional to the height. It will be maximized at the highest point and minimized at the lowest point. Well done. Let's do this and actually see how this works. So we need to minimize V, the gravitational potential energy, subject to the constraint g of xy equals x squared plus y squared is equal to a constant value 1. So our constraint is just the physical position in which the bead is allowed to move. And now we just go back and we go, okay, well, let's set it up. What is our f? Our f is the thing we want to minimize. So in this case, it is the gravitational potential energy. Our g is the constraint, which has to be the thing that's equal to a constant. So in this case, it's x squared plus y squared. Or it could be x squared plus y squared minus 1 if you just shove everything over to one side. The math still works because gradients don't care about constants. So grad of f equals lambda grad of g gives me grad of f, the partial derivative with respect to x is 0. Partial derivative with respect to g is mg. And that is equal to some multiple of grad of g. Derivative of g with respect to x is 2x. Derivative of g with respect to y is 2y. Okay. And our constraint is that g is equal to 1. So I have three equations. 2x lambda equals 0, 2y lambda equals mg, g is equal to 1. So three equations. 0 is equal to 2 lambda x, mg is equal to 2 lambda y, and x squared plus y squared is equal to 1. My constraint equation, because don't forget, I also have the equation that g is equal to 1. If you solve that, you're all very clever. I think you can do this. I believe in you. You get x is equal to 0, y is equal to plus or minus 1, and lambda is equal to plus or minus mg over 2. Lambda has a significance, but it's like not super relevant to what we are trying to achieve. And you can see that this picks out 2 points. X is 0 and y equals 1, which is a local maximum. And x equals 0, y equals minus 1, which is a local minimum, which means that this is where the bead will want to sit. This is the equilibrium position. So that's nice. The thing that I kind of want to draw out of this is we didn't have to mess around coming up with the constraint. The constraint was suggested by the problem. This is going to be the case more and more. We'll go back to the matrix examples we just did. Oh, yes, question. Good question. Good question. It will, assuming everything is sufficiently continuous and we don't have any non-analytic weirdness, which, remember, is the assumption we're making throughout this course, yes, this will spit them all out. And we're actually going to do an example later which spits out 14 different critical points. Yeah. Okay. Of course, then the question, and we will talk about this in the next hour, is what do we do with them? How do we classify them? We could eyeball that this was a max or a min, but that won't necessarily be the case, especially when our constraints don't leave us with a one-dimensional system, so saddles are in play as well. All right, you're all having a moment. Okay. So previously, we looked at the behavior of the trace of M. We considered this behavior M equals A, B, C, D, and we said, well, we can find that the determinant has a critical point at 0, 0, 0. Here we want to ask something slightly different. What is the extreme value that the trace can take if I fix the determinant to be 1? And that's actually not necessarily so obvious. I mean, it's probably what you think it is, but we should show it. So we need to, I saw at least one face of someone who said, I have no idea what you think I think it is. That's fine. So we need to find the extremer, and to do that we need to set up our system. So remember, start with the thing you're trying to optimize. The thing I'm trying to optimize is the trace of M, which is equal to, tell your neighbor what the trace of a matrix is. It's one sentence. I saw some hand gestures going like this. Yes. The trace is the sum of the diagonal entries. That is all. Trace is a weirdly important quantity. You'll learn more about that in 2922. We're just going to calculate the thing. So this is a function of A, B, C, D. And our constraint, G, A, B, C, D, is going to be equal to the determinant of M, which is, of course, AD minus BC, which we are fixing to be 1. So we have an F, a thing that we are trying to optimize, and we have a G, a thing that we are trying to constrain. So our system, going back to the set of equations, we have this, and we have G is equal to 1. Okay, so I'm not going to do these calculations out too carefully because you've done these a bunch of times. The derivative, the gradient of the trace, 1, 0, 0, 1, and that's equal to the gradient of the determinant, which we've already figured out. Gives us that. And now we have our system in the usual way. So, 5 equations, 5 unknowns. First equation, 1 equals lambda d. Second equation, 0 equals minus b. Third equation, 0 equals minus c. Fourth equation, 1 equals lambda a. And the fifth equation, the constraint, AD minus BC equals 0. Solution. 1, thank you. Good. Is 1. So our solution, at the very least, B is 0 and C is 0. That's nice and easy. Which means that this term knocks off, which means we get A times D equals 1, which means we get AD is 1, A is 1 over lambda, D is 1 over lambda, and solving that, and I think I heard someone say it, so we get 1 over lambda squared equals 1, or lambda equals plus or minus 1. So we get 2 solutions, A equals 1, D equals 1, and A equals minus 1, D equals minus 1, which is to say 1, 0, 0, 1, which has trace 2, and minus 1, 0, 0, minus 1, which has trace minus 2. No worries, it happens. And we can see just from the geometry of the system, this will be a max and this will be a min. Now I'm making that claim, and we'll talk a bit how we will calculate that later on, But you should hopefully see that as you vary the odds and ends, you can't make the trace go any higher than that. Have a bit of a mess around with that if you want. Okay, so this is nice and practical. We can say things about stuff. Let's try and do a system which maybe we would have struggled to do last year, and let's actually talk about the question that was asked before: can we pick out every extreme value? And then let's ask ourselves, how can we tell what those extreme values are? But we're about to dive in. Now is a good time for a 2-minute break to stretch your legs. I note for the people watching at home that we are still recording, so that is good. All right, take 5, be back in 5 minutes, and we'll start proper.
Sorry, just I won't take too long. I mean, I might, but like it's dragging on, then I'll really don't worry. Yeah, actually, yeah. Sorry, yeah.
Where are you who just asked me that last question? These are saddles, not a max and a min. My bad. We'll show how to classify those in a bit. Yeah, these are saddles. Okay. All right, yes, hit me. All right, I've got 305, so let's roll it back in together. And let's do a bit of a mea culpa. I threw max and min on at the end, and as pointed out to me quite rightly, that is not necessarily the case. These are in fact both saddles. So that's nice.
Also,
I do enjoy being wrong.
on the notes, when we post them,
Started talking. So we have this. All right, so needless to say, this is a very instructive. It was a mistake. I'm not pretending I did it to teach you something, but I'm certainly going to take advantage of it. We do need to find a better way to classify these rather than just eyeballing the system and taking a guess. So that is one of the things we're going to do, and we're going to start by doing it on the next example. So the next example is my least favorite kind of problem, a very artificially created geometry problem. We're going to say, all right, what is the minimum distance on this ellipse to the origin? Basically the same as our line, except ellipses are nastier. Now, without too much guesswork, the reason we pick these is because they're nice and they're simple and we can kind of envision what's going on. And you can imagine as that magenta circle grows, it will first touch the ellipse at 2 points that will be a minimum. And then as it grows further, it will touch the ellipse at this point, which will be a local maximum. And then as it grows further, it will eventually touch the ellipse at this point, which will be a local maximum / global maximum. So we've got our ellipse, and it's x minus 1 all squared over 16 plus y squared over 3 equals 1. You could do this using single variable methods from first year, and it would be deeply unpleasant, and I don't think you want to do that. So what we're going to do is instead set this up as a Lagrange multiplier problem, but the question we're eventually going to ask is, could we have picked whether these are max or mins? So we want to minimize the distance to the ellipse. So we want to minimize our function f, which like before is the distance squared, so we're just going to call f is x squared plus y squared. So we want to minimize f, and we want to do it subject to the constraint which the ellipse equation gives us. So g is equal to x minus 1 all squared over 16. I had meant to erase this. Pretend you never saw that. Plus y squared over 3. I write lectures by writing the whole thing, putting that to one side, and then erasing all the bits I want to do in class. So that's why sometimes that can happen. So we do that, and we didn't have the answers written in front of us, so we go and do all of the calculations. Grad of f equals lambda grad of g. We've done enough calculations of these quantities now that I'm going to skip through to what you find. The first term of our Lagrange multiplier equation, x minus 1 over 8, which I'm going to call equation 1. The next one is 2y is equal to 2 lambda y over 3, which is equal to equation 2, which is going to be the useful one. And our constraint, which is a bit unpleasant, x minus 1 squared over 16 plus y squared over 3 is equal to 1, which I'm going to call equation 3. So this was our constraint. Now equation 2 tells us a lot. This is a nicely constructed problem because equation 2 tells you that either lambda is equal to 3, in which case we get 2y is equal to 2y, or y is equal to 0, in which case we get 0 is equal to 0. So equation 2 gives us two options. Y equals 0, which we're looking for a minimizer, so that's wrong. And lambda is equal to 3, which by process of elimination is going to be right. Again, we couldn't have known this if we didn't have a picture we could look at. I can see that y equals 0 is not going to give me a minimizer. And if I had just wanted a minimizer, I could just throw them away. But maybe I won't know that. So if I solve the system with lambda equals 3, then the other equations are a bit less nice. But what you get is x is equal to minus 3 over 13, and y is equal to plus or minus 3 root 51 over 13. So you probably did that in your head. I did not. Which gives us these points here. So this is x is equal to minus 3 over 13, y is equal to minus 3 root 51 over 13. And of course, this is the other one. So we've picked out these 2 points, and we know by looking at that they're minimizers, but information is free. We have y is equal to 0. We should at least know what it's doing. So let's follow that pathway through and see where it takes us. So in this case, I have the same equations, but I am going to choose y equals 0 instead. Well, in that case, if y equals 0, it vastly simplifies the second equation, because I get x minus 1 squared over 16 equals 1. I'm not even going to calculate the Lagrange multiplier. It's just a tool to help me set up the problem. So y equals 0 gives 3. Y equals 0 into 3 gives x equals minus 3 or x equals 5. Because this has to be x minus 1 squared over 16 equals 1, so this has to be 4 squared over 16 equals 1. So we either have x equals 5 or x equals minus 3. Okay. There's now the third example. We've done plenty of these. But what we want to do is classify our 4 critical points. Sorry? Yes. I didn't label both. This is also a min, that is true. Yes. Good. Good. So we're going to want to classify this. Unfortunately, classification is not so simple, but it does tend to reduce. What you have to do is you have to move on to your constraint set and do an unconstrained optimization techniques on that set. So what do I mean by that? Well, this is nice because our constraint set is one-dimensional. So what we're about to do is going to reduce to a one-dimensional optimization problem. So let's take xy equals minus 3, 0. We found that as one of our options. We'd like to know what it is. We're pretty sure from looking at it that it's a local maximum, but maybe I'm incredibly bad at interpreting pictures. So we know f is equal to x squared plus y squared, and g is equal to x minus 1 squared over 16 plus y squared over 3 equals 1. And then what we have to do is basically exactly what we would have done in first year. We're going to say, well, x is equal to 1 minus 4 square root of 1 minus y3 over 3. This could have been a plus or a minus. If I try and rearrange this constraint equation, I get a plus or a minus. Why did I pick the minus? Tell your neighbor. Tell your neighbor? Don't tell your neighbor. Hands up who thinks they know why this is a minus sign. Yes?
We are thinking that x equals minus 3.
Fantastic. Exactly right. X is negative. It's less than 1. If I wanted to pick out this one, x would be positive, plus 1. I heard people say minimizer. You are overthinking it. It is literally just the geometry of the problem tells us that we are looking at the negative branch. So some geometry still required. Pick negative sign. Since x is less than 1. Okay, so near minus 3, 0, we write f tilde equals f of x of y, y. So we're saying f tilde is a single variable equation expressed in terms of y. We're actually saying f is a graph of y for what it's worth. But now we have a single variable function, and we can do single variable optimization. So f tilde is equal to minus 1 minus 4 square root 1 minus y cubed over 3 all squared, which was our x squared. Yeah, it probably should. Good. Thank you. Plus y squared. And now, what do we do? Question or? Should be a plus 1, yep. Thank you. I heard expand. I'm just going to say it's the words written immediately below. We just do the second derivative test. We learned it in first year. Why waste it? F dash dash, F dash dashed, and we are interested in y equals 0, is equal to minus 6. So, if the second derivative is negative, I even popped this up on the board yesterday. Therefore, this is a local maximum. This was pretty easy because we were able to reduce our problem to a one-dimensional optimization. However, if I go back to, say, this example, then I won't be able to do that. I will have to reduce my problem to a three-dimensional optimization. But we can do three-dimensional optimization now using the methods that we learned yesterday and this morning. So we have a tool in our kit bag to enable us to do that. Now, I don't want to do that for this problem. I want to do a new problem because we can actually unpack the geometry of this one a little nicer and see what's going on. So we're going to say we're going to find the extrema of this function, subject to it lying on the three-dimensional sphere S2. I have a note here that says skip this if I'm running out of time. But the good news for me is that I'm not, so we get to do this problem instead. All right. We've done Lagrange multipliers like 4 times already today. Let's skip through the easy part. Grad of f is equal to lambda grad of g, and g is equal to 1. F is 2xyz, and g is x squared plus y squared plus z squared, distance squared in R3. This problem is not meant to inspire you as to why this is such an exciting method. Okay, so this gives us 4 equations and 4 unknowns, because remember we have 3 variables and we're also going to want to solve for the Lagrange multiplier. So we're going to get 2yz is equal to 2 lambda x. We're going to get 2xz is equal to 2 lambda y. And we're going to get 2xy is equal to 2 lambda z. And we get the constraint x squared plus y squared plus 1 is equal to 0. This has a lot of possible solutions. I believe it has 14. So we are going to go through and we are going to pick them out, but I'm going to be a little more careful about solving this system than I've been with the ones I've done so far. If lambda equals 0, then we have some solutions. If lambda equals 0, then either 2yz is equal to 0, 2xz is equal to 0, or 2x, then we need xy to be 0, xz to be 0, and xy to be 0. The only... Yes? Sorry? Yeah, sorry, z squared equals 1. Thank you. Good. The constraint equation. So, for all of these things to be 0, then at least 2 of x, y, and z must be 0. If x and y is 0, then I've got y is 0, x is 0, they're both 0. If x and z is 0, then z is 0, they're both 0, y is 0. So essentially, if lambda is 0, then at least 2 of x and y and z must be 0. And if 2 of x and y and z is 0, then the other one has to be plus or minus 1. So that gives me 6 solutions. I get x, y, z is equal to plus or minus 1, 0, 0, 0 plus or minus 1, 0, or 0, 0 plus or minus 1. And for each of these, the Lagrange multiplier is 0. Okay, but if the Lagrange multiplier is not 0, then none of these can be 0. Because if any of these are 0, then either they're all 0, in which case this can't be satisfied, or I will get at least one of these equations saying I have 0 equals not 0. So if the Lagrange multiplier is 0, then none of x plus y or z can be 0. We're going to assume that they're all non-zero and see what we can find. In this case, we can say something about the Lagrange multiplier at least, which is that it is yx over z, which is equal to xz over y, which is equal to xy over z. Nope, got that one. Yz over x. And now I can use this, do a bit of solving. So this is equation 1, 2, 3, 4, and if I equate them, I'll get x squared equals y squared. If I equate 1 is equal to 3, I get x squared is equal to z squared, and I get y squared is equal to z squared. As you can see, solving nonlinear equations is a lot harder than solving linear systems. For example, if this was a linear system, it would have 1 solution, 0 solutions, or infinity solutions. This, as I mentioned, will have 14, which is notably not any of those numbers. Nonlinear problems are much harder to solve and generally have to be pretty bespoke. I'm working through this one because it's not just a direct application of methods you've used in the past. It's just like every nonlinear... In math, every linear problem is done with linear algebra, and every nonlinear problem is basically a unique horror that you have to carve through. Like, that's your choice. As we'll learn when we do differential equations. Okay, so x squared is equal to y squared is equal to z squared, which means if we put our constraint together, we get x squared plus y squared plus z squared is equal to 1. Or if you like, 3x squared is equal to 1, which is to say, I get, where each of these signs can be chosen independently, plus or minus 1 on root 3, plus or minus 1 on root 3, plus or minus 1 on root 3. Let's say, or, this gives me 2, 4, 8 solutions. 2, 2, 2, 6 solutions. 8 plus 6, 14 solutions. So we're on track. There are 14 extrema. What a silly number. Okay. At these three, the value of the thing we're trying to optimize is 0. At this one, the value of the thing we're trying to optimize is plus or minus 2 over 3 root 3, depending on how many minus signs you took. So, max, min, saddles. In previous examples, we kind of were able to see, that's a maximum or a minimum. But as we know, as soon as the number of dimensions makes it difficult to visualize, it's easy to get this wrong. Let's do it right. And as a nice exercise, I don't think I did it. Yeah, go back and try this for the trace determinant example. We're going to consider the critical point at 1, 0, 0, so the first one. And we kind of have to do what we did before. We have x is equal to the square root of 1 minus y squared minus z squared. Why did I pick the positive square root? Because x is positive. Okay, because it could have been plus or minus. I've taken a square root because I've just rearranged the constraint equation. Remember, this came from x squared plus y squared plus z squared is equal to 1. And we also have, for what it's worth, lambda is equal to 0. That won't really matter, but completion. So we'll define our f tilde of yz is equal to f of x of yz, which is equal to, bit of algebra, 2yz square root of 1 minus y squared minus z squared. Because remember, f was equal to 2xyz. Little bit of complicated terminology, just letting us know what our variables are. This is really bookkeeping more than anything else. Taken this x, put it in here, got myself a function of 2 variables, and now I can just classify the critical point using all those cool techniques I taught you yesterday. D squared of tilde, we are at y equals 0, z equals 0. Equals 0, 2, 2, 0. So lambda 1 equals 2, and lambda 2 equals minus 2. This is a saddle. So if you want to classify, Lagrange multipliers give you a nice, easy way of finding critical points. They don't help you in any way classify them. If you want to classify the critical points, you need to somehow reduce back the dimension of your problem and apply the unconstrained classification theorem that we learned earlier, that we proved earlier today. There is a better way to think about classification. You've now met classification. We want to think about it a little more geometrically, at least. But to do that, we need to define a new quantity. And this new quantity is known as the Lagrangian. The Lagrangian function, which we call L, is equal to f minus lambda g. And as I'm sure you can see, the first of our equations was simply taking the grad of L. So if we want to start thinking about this geometrically, if you want to say, well, how could I find the classification with Lagrange multipliers? I thought the whole point of this was to not have to do unconstrained optimization. And you can. You've got to use some properties of the Hessian. So, I mean, we're still doing unconstrained multiplication, unconstrained optimization, but we want to think of it using the same kind of tangent plane ideas we use to construct Lagrange multipliers. So we do what we did. We evaluate the Hessian at the critical point P. And remember, we've reduced it back to a dimension. And what we do is, we do exactly what we are doing when we do classification in general, which is, we say, well, what are all the tangent vectors of the constraint at P? So we haven't reduced the dimension of f. We're not operating on f tilde here. We're operating on f in general. So not f tilde, f. And we're saying, okay, well, the tangent vectors of f, the tangent vectors of g, which we know should be the same as the tangent vectors of f, at P. Well, let's look at this thing here. So v is any tangent vector. So v is any element of the tangent space at that point, and this is our Hessian. If every element of the tangent space is positive, as we learned from the classification theorem, if it gives us a positive value, it's a local minimum. If every v from the tangent space is negative, then every direction we go will give us a local maximum. And because you can, if it's sign indefinite, which is to say it could be plus or minus, depending on which v you pick, then you have a saddle with the usual condition that if you get zeros, life is painful. Okay, so what I mean by tangent vectors, I mean all non-zero elements of the tangent space. And we can see this working. Let's take another look at the ellipse problem and think about it through this lens. So we're going to take another look at our ellipse problem, and we're interested again at minus 3, 0. And we've already showed that it's a local maximum. But what we're going to do is we're going to say, all right, let's construct the Lagrangian. The Lagrangian is f minus lambda g. And you will remember that f was x squared plus y squared, because it was the distance from the origin, minus lambda times the constraint, x minus 1 squared over 16 plus y squared over 3. And I'm going to ask myself, well, what is the tangent plane at that point? So here I'm doing the tangent plane because I'm just connecting it to the point, but really I'm interested in the direction. So what I actually care about is the tangent space. which is, of course, the tangent plane is nothing if not the tangent space glued to the point. So the tangent space is just vertical vectors. So we calculate the Hessian at that point, at 3, 0. The Hessian of the Lagrangian at minus 3, 0 is equal to 2 minus lambda over 8, 0, 0, 2 minus 2 lambda over 3. And I want to evaluate that at lambda equals 12. So now I actually have to use the Lagrangian multiplier. That is actually part of the setup for this approach. We can't escape the Lagrange multiplier here, but we calculated it when we were looking for the extrema, and we get 1/2, 0, 0, minus 6. Now, previously when we've gotten this Hessian, we've calculated its eigenvalues. That's actually not what we're doing here. What we're doing instead is asking about the tangent space. So the tangent space is all of the vectors from 0t, where t is an element of R, and we exclude 0 from this definition. Well, no, we'll exclude it below. The tangent space is just this, but here we exclude v equals 0 from this definition. Just makes life easier. So we're going to be pulling out every non-zero vector from the tangent space, and we're going to say, well, what is v transpose times by the Lagrangian of L evaluated at minus 3, 0 times by v, which is equal to, okay, so v transpose could be 0, 1, could be 0, minus 2. I don't want to mix blue and green. Could be 0, 1, could be 0, minus 2, could be 0, 10. Could be anything, but it's got to be vertical. So it's going to be 0t times by 1/2, 0, 0, minus 6 times by 0t, which is equal to minus 6t squared, which is always negative. There is no tangent direction I can take where my f increases. And therefore, this must be a maximum. So what this does is kind of skips a lot of the overhead and gets straight to the classification using what the concept of the tangent space was involved with in the construction of this method. So let's now revisit the slightly nastier problem that we did, which was 2xyz on the three-dimensional sphere, and ask ourselves, how would we tackle this problem? Slightly tougher tangent space. We start by constructing the Lagrangian. F minus lambda g. So, the Lagrangian of L is equal to minus lambda zy, sorry, I'm just copying this out exactly because I will transpose this incorrectly if I'm not careful, x, y, x minus lambda. And we're going to look at the one we did already, because we know what that should be, but it would be a really nice exercise for you to go and try the other critical points, particularly the ones at plus or minus 1 on root 3, all of the variants of that. Okay, so we're interested in x equals 1, y equals 0, z equals 0. So the Lagrangian at that point is, remember, our Lagrangian was y equals, was lambda is 0. So this becomes 0, z is 0, y is 0, z is 0, lambda is 0, x is 1, 0, 1, 0. Okay. So, you know, this is it's got a whole row of zeros. Seems a little bit degenerate. It doesn't really matter because remember, we're interested in the tangent vectors and the tangent space. So we are interested in this point here, 1, 0, 0. And the tangent space, which we calculated last week, we know what the tangent space at the, planned ahead. We know that the tangent space of a sphere at this point is just going to be any vector in the y or z direction. So any vector in the z direction, any vector in the y direction will be tangent to the sphere at that point. So the tangent space is two-dimensional. So the tangent space is going to be equal to, I like to write this as t times by 0, 1, 0 plus s 0, 0, 1, just to really reinforce that we are looking at a vector space. Any vector of that will be perpendicular to the surface at the point we care about. And now we evaluate vt d squared lv, which is equal to 0ts 0, 0, 0, 0, 1, 0, 0, no, 0, 0, 1, 0, 1, 0, 0ts, which is equal to 4ts. 4ts can take positive or negative sign depending on the choice of t and s. So what does that mean it is? Yell it out. It means that we are looking at saddles, which is good because that's what we found before. It's nice when our two different examples agree with each other. You can absolutely do this for the 1 on root 3 examples, and it's a really nice exercise for you. It's an exercise in two ways because you actually have to think a little bit more carefully about the construction of the tangent plane. So I really strongly recommend trying this yourself. Try plus or minus 1 over root 3, plus or minus 1 over root 3, plus or minus 1 over root 3. You should find that if there is an even number of pluses, an even number of minuses, so none or 2, then it's a maximum. And if there are 1 or 3 minuses, then it's a minimum. But that's a really good exercise to test, do you have a really clear picture of tangent spaces? Do you have a clear picture of Lagrangians? Now, this quantity L is called a Lagrangian. Has anyone seen that word before? Just hands up if it's a word you've encountered. Did anyone see it going through the course catalog looking at 3,000 level subjects? So you might notice that there's a 3,000 level subject called Lagrangian and Hamiltonians. Lagrangian and Hamiltonian dynamics. That really is the study of the consequence of these Lagrange multipliers on differential equation dynamics. It's a really interesting class, and it's all about what about these ODEs subject to constraints? Constraints like conservation of energy, constraints like conservation of momentum, all of these really important equations. Equations that have all of these conserved quantities that we study with Lagrange multipliers are often called integrable systems. And that's what that third-year class is all about, is taking these Lagrangians, embedding them in a differential equation setting, and seeing what incredible things that tells us. I actually thought about writing an assignment question on that, where you show that the geodesics on a sphere are great circles, which absolutely is something you can do with Lagrange multipliers, but I decided it was maybe a little bit mean. If you are interested in that, though, it is well worth a read. This is an incredibly powerful idea. An interesting, and this is, what I'm about to show you is actually, I'm not kidding, the example that convinced me when I was a PhD student that Lagrange multipliers were important and not just some sort of neat little artifact. Because I was auditing a course in the UK on information theory, and I ran into this problem, which is, okay, so we have a particle in one of n states, and each state I has energy EI. The average particle energy in the system is E dashed. What is the probability distribution that maximizes entropy? We are about to derive a probability distribution from almost no information. And that's a really powerful thing to be able to do. Let's track out what we have. We know that the probability of being in the ith state is pi. And because pi is a probability, we know that if you take the sum, I equals 1 to n of pi, that's equal to 1. That's how probabilities work. People in Math 2911, that will be useful for you. Stat 2911. The average entropy, the average energy of a particle is actually an expectation. It's an average, which is to say that the probability of being in a state times by the energy of the particle in a state should be some average E, which we have is E hat, the average particle energy. So we have two constraints. And this is another important thing about this example that we're going to do, is we're going to introduce a second constraint into the system and see what that does. And finally, we have the two constraints. We've said that the average energy is E hat, and we've said that the ith state is Pi. But we also have the formula for entropy. This is really neat. It is essentially a mathematical result. It's called Shannon's entropy formula. Well worth a read if you find anything about information theory interesting, which is P log P. So the total amount of energy in the system is P log P. And you can imagine that, because if everything is the same, then P is 1, log of P is 0, and there is no entropy whatsoever. So it's a measure of how random your system is. What we are doing is deriving one of the most fundamental ideas of statistical mechanics. So we have constraint number 1, we have constraint number 2, and we have our thing we want to minimize, maximize. Minimizing entropy is very easy. You just make everything the same. So we want to maximize this. So two constraints are actually allowed. You can have two constraints. You can even have n constraints. Now, to manage this, you kind of need to not forget about the geometry, but it's a little harder to envision what this means in terms of just tangent spaces of level sets. But once you understand the formulation of Lagrangians, you can actually just say that the gradient is a linear combination of the constraints of constraint gradients. Which is to say, our Lagrangian, if we had just one constraint, it would be easy. It would have been f, the sum from I equals 1 to n of pi, pi log pi. Because p is between 0 and 1, the log of it is negative, so the other negative is just there to make entropy positive. Minus the constraint, the sum from I equals 1 to n of pi. And we're going to put minus 1 so it equals 0. It's a helpful thing to do. It will vanish out, but it makes it easier to kind of read the constraint out of the equation. Except we're also going to have a second constraint, the sum from I equals 1 to n of pi ei minus e hat. It is beyond the scope of the course for me to tell you why this is true, but it is just geometry, but you kind of forget all the pictures and just work through the geometry. You can look it up if you want, or you can trust me, I'm very clever. So now we have n plus 2 equations and n plus 2 unknowns, and you could just keep whacking constraints on there. There's no limit, other than you probably want something left at the end, so you don't want to put too many constraints on. But it is totally free to keep doing that. Okay, so I'm going to copy that to the next page. And we're going to power through and see if we can get some kind of distribution to come out. So we do exactly what we would normally do and set the gradient of the Lagrangian to be 0. If we just had one constraint, that would be saying that the gradient of f is lambda times the gradient of g. But because we have two constraints, we're saying the gradient of f is lambda times gradient of g1 plus beta times gradient of g2. So we evaluate our gradient, and we get a different value for each pi, right? So what we're looking for is what are all of the pi's. So the ith element is minus log of pi minus 1 minus lambda minus beta ei, and we want to set that to be 0. So that is n of our equations, one for each possible state. And if we solve that, then what we get is that pi is equal to e to the minus 1 minus lambda minus beta ei. And we can start to see that we might be looking at some kind of exponential-ish distribution. And you're not wrong. This is going to be a maximum. We aren't going to classify this today, but it's a nice exercise. It's not that hard. This will be a maximum. But we're not going to show that. And now we go and we apply our constraints. Our first constraint says that the sum of all the probabilities has to be 1. So our first constraint says that the sum from I equals 1 to n of e to the minus 1 minus lambda minus beta ei is equal to 1, or e to the minus 1 minus lambda, sum from I equals 1 to n of e to the minus b ei is equal to 1. And this is just a number. I mean, we don't know beta yet, but we know ei. So we can easily just work that out, and we can invert this whole thing, because this tells us how we can eliminate lambda. So we use this to eliminate lambda. And what we get is the probability of being in the ith state is e to the minus b ei over some big number z, where z is equal to the sum from I equals 1 to n of e to the minus bi. So this number z is related to the total energy in the system. Now we still need to find this beta. Unfortunately, we have one more constraint, and that's exactly what we will do. Although now we're going to cheat just a little bit because the algebra is nasty. Constraint number 2 told us that the average energy in the system is pi ei, which is equal to E hat. Now, we know pi from before. We figured out pi. So we're going to sub that in, and we get the sum from I equals 1 to n of e to the minus b ei all over capital Z is equal to E. In theory, this is something we can solve. We know E, we know EI, we know Z, although it does depend on beta, but in theory this is something you can invert. But inversion is hard. So instead we're going to use some physics to cheat a little bit, because in physics if you can't solve for something, you pretend it's what you defined it to be. And in fact, the definition of temperature is nothing more than the derivative of the Laplacian with respect to E hat, which is 1 over T. T is temperature. That's what temperature is. Temperature is just a statistical mechanics quantity. It's how much energy there is in the system, more or less. But with all of the scalings that make that work. So from our equation for the Lagrangian, if we take partial Lagrangian, partial E hat, it doesn't take too much effort to show that's equal to beta, so therefore beta equals 1 over T. You might argue that we haven't solved this. We've written it in terms of stuff you can measure, which is good enough for physics. So you put all of this together, and you get e to the minus ei over t, all over z, where z is the normalization constant, I equals 1 to n, e to the minus ei over t. Boltzmann won the Nobel Prize in like 1901 basically for coming to this result. This is the Boltzmann distribution, and it is the statistical mechanical expected maximum entropy distribution of particles in a vacuum. And we defined it not by really incorporating anything probabilistic, but by just saying, well, probability works, we have an average energy, and we want to find the most disorganized system we can. A last thing before you go, you can do this in a continuous setting. All of this stuff that we've done in terms of Lagrange multipliers has been in discrete points, but there is work on this in a continuous setting, which if you ever run into the concept of the calculus of variations, that's what this is. It is saying, well, what if instead of a finite set of points, a finite number of dimensions, what is the continuous, which is to say infinite dimensional setting? Because you can imagine if it was infinite dimensional, then n goes to infinity. I have an infinite number of equations and an infinite number of unknowns, and probably I'm going to run into problems. And you do, but it does tend to a continuous methodology, the calculus of variations. Fun fact, using a very similar argument to this, you can use that to prove the central limit theorem. Like, it is really powerful stuff. Almost all of pre-19th century physics was studying how to embed physical laws in the context of the calculus of variations. It's a really important topic that probably you'll never meet as an undergrad. I'm just telling you this because, you know, you're in the advanced stream, you might meet this one day, is that the calculus of variations really is the continuous equivalent of the discrete questions we've been asking here. It's pretty neat. It's well worth the read if you're interested in that sort of thing. Okay, so we're done. Next week, we are going to move on from optimization and we're going to move into multiple integrals. I consider this to be the 2 easier weeks of the first half of the semester, but that doesn't mean you can zone out. I'll see you next week. We'll do lots of tedious integrals. You'll all have a great time. Or I'll see you in like an hour.
I've got my
It's always going to have a zero.
I just didn't want to eliminate the possibility that not anymore. I can arrange another time if you are absolutely unable to make that, but I will expect you to be absolutely. At the time. Well, in that case, I see what we can do. Tell me and I'll make that.